Hello viewers, welcome to today's lecture on real-time operating system for embedded applications. In the last lecture, we have discussed about two applications. Essentially, they are embedded applications. And there you have seen the applications are developed, or rather the application program are directly developed on the hardware. So this is the hardware, and the application program directly controls the hardware. So this we can represent this in this manner. That means the application programs are directly controlling the hardware resources like I/O devices, memory devices, and various other things. There is nothing in between the application program and the hardware. And this particular situation is holds good for simple applications, or in other words, simple applications can be implemented in this manner. In fact, most of the embedded applications are implemented in this manner. However, as the complexity of the application program is increasing, and you will find that new special type of applications which are real time in nature are gradually increasing. That means that embedded applications are used in many real time applications and in many diverse complex applications. In such a situation, it is necessary to have something in between. That means you will have hardware somewhere here, then you will have something in between, intermediate software. So intermediate software, and then you will write application software on top of this intermediate software. This is where the application software will be written. So this is how it can be done. You may be asking, what is the purpose of this? Why it is done? The reason is this way. There are several reasons for this. Number one is this provides an interface between hardware and the user. That means user that does not directly interact with the hardware. In other words, the application software or program does not interact with the hardware directly. It does it through some intermediate software. Also, it provides an user-friendly environment. Whenever the user has to interact directly with the hardware without any software in between, it may be very difficult, particularly for a beginner who is for the first time developing an application software, and if the problem is complex. In such a situation, this is very much useful. So it provides an user-friendly environment. Also, it allows easy implementation of applications. Applications can be very easily implemented. So it is essentially a kind of tool that helps us in developing the application programs. In addition to this, it also performs several other functions such as resource management. There are various resources like CPU, processor, memory, I/O devices, and so on. These resources are to be managed efficiently so that their utilization is good. So this is one another objective of this intermediate software. And then uh, effectively what it will do, it will control execution of a number of tasks or maybe subtasks and allow inter-process or inter-task communication in a very convenient manner. So these are some of the functions to be played by this intermediate software. And since a good number of applications are turning out to be real time in nature, and the functions that is being performed by the software is essentially same as the operating system, that's why this intermediate software can be called as real time operating system. So that intermediate software that will be used between the application programs and the microcontroller can be called as real time operating system. So it is a kind of operating system specially designed for real time embedded applications. So before we discuss about the real time operating system, let us now consider a brief history. Let us consider the evolution of operating system. How operating system has evolved from a very primitive type into a very sophisticated one, which are used in present day computers. After giving an overview of this, we shall consider the real time operating system. The first one, the first operating system which were used in 60s were very simple and primitive in nature. That was known as batch processing systems. Those operating systems were known as batch processing systems. In those days, the jobs were submitted with the help of punch cards. Suppose a number of users, each of them submitted their jobs using punch cards, say n jobs are accumulated. Then what was done, the jobs were processed in a batched mode, and the way it was done is like this. Uh, Suppose this is the memory, main memory of the computer. As you know, to execute a program, it is very much essential to load it in the main memory. So you have your batch monitor, that is your operating system, and one of the job which is under execution is loaded in the main memory. And how it is done? Then there is a some kind of start of job, start of batch, you can say, which was initiated by an operator, and then you have got, say, job 1 is executed first, then job 2. In this way, job n is executed. That means all the jobs are executed one after another till you reach the end of end of batch. That is another kind of, I mean, some punch cards which are which signify as end of batch. So now what is the how it is happening? You see, after the computer encounters the start of batch punch card, the first job is loaded from the punch card machine into the main memory. This is your main memory. Then it is executed, and after execution of job 1, then job 2 is again loaded into the main memory, then it is executed. In this way it goes on till job n is reached, and when all the jobs are processed, we reach that end of batch card, and then we say that the all the jobs have been executed. Now when the user gets its response or result of the program, so in those days the scenario was like this. Possibly in the evening they used to submit their jobs. In the night the computer used to run all the jobs in batched mode, and next morning the user were collecting their results when all the jobs have been executed. Now what is the disadvantage of this particular mode? First of all, it leads to poor processor utilization. Why? As you can see here, the it is loading one job, and a particular job may require some IO operations. So when the slow IO operations are going on, the CPU is remaining idle. Moreover, when one execution of one job is over, another job can be started, execution of another job can be started only after loading it from the from the through the punch card machine into the main memory. So lots of times are wasted, and the CPU, particularly the precious CPU time, is wasted. That's why it has got poor processor utilization. Another important disadvantage of this particular approach is it has got long turnaround time. What is turnaround time? In this case, what happens? A particular user submits its job, then waits for the result. Now, the time between the submission of job and getting the result is the turnaround time. And obviously, in this case, irrespective of when the job is submitted, the user has to wait for the entire period, and only after all the jobs are executed he will get the result. As a result, the turnaround time is very long. It has got a very long turnaround time, and as a consequence this batch processing systems uh, were uh, were removed, and a new technique known as multi-program system operating systems were developed. So in this case, what was done, uh, first thing that was done is all the jobs were loaded into the main memory. That means apart from the operating system, that is your multi-program supervisor, that is your monitor program or the operating system, you can say. Apart from this operating system, for multi-programming operating system, you have got job 1, job 2. In this way, all the jobs, job n, are all loaded into the main memory. So here we find that the all jobs are memory resident. That means in the beginning itself, all the jobs are loaded into the main memory. That means the time needed to load the job from the slow IO device like punch card to the main memory, that time is saved in this particular case. And so it is better than the earlier batch processing systems. Second thing is, in this particular case, usually separate IO processors are also used. What is the advantage of this, having a separate IO processor? You have got the CPU and you have got separate IO processor. Now, what is done, jobs are classified into two types. One is your CPU bound, another is IO bound. Now suppose when the job is executing and it requires some IO, then what can be done? If is some IO, then job 2 can be can use the CPU, and job 1 can use the IO. That means some kind of parallelism is possible. And by choosing a good mixture of CPU bound jobs and IO bound jobs, it is possible to improve the utilization of the CPU. So that is the advantage of this technique. And some other features of this multi-program programming operating system is it uses priority based job scheduling. As we have seen, all the jobs are loaded into the main memory. So there is a scheduler which will choose a job which has highest priority. So in this way, jobs with highest priority are scheduled first and they are executed first. Usually, IO bound jobs are given higher priority for better CPU utilization or better throughput. Better jobs are given higher priority. And it has been found that by doing that, you get better CPU and IO utilization. So, these are the typical features of this multi-programming system, and we find that in this case the advantages are better CPU utilization. So, you have got better CPU utilization in this case. Now, although better CPU utilization is achieved, the turnaround time is still not very good. Why? Uh, Turnaround time is not good. In this case, even in this case, as you can see, the jobs are executed one after the other. If there is a big job, that job will monopolize the CPU, and as a consequence, an user that user having a very small program requiring small execution time may have to wait for a very long time. So even in this multi-programming systems, multi-programmed operating system, the turnaround time is not good. So to overcome the limitations of the multi-programmed operating system, another operating system was developed which is known as time sharing systems. What is done in time sharing systems? Here the main feature is that there is no priority of jobs. There is no priority. That means all jobs are considered to have same priority. There is no higher priority for any particular job. How it happens? When a job is submitted, that means it becomes a new job and it is admitted to a new state. It goes to a new state known as ready state. This time sharing system can be best explained with the help of this 5-state process model. Here you see we have got 5 state: new, ready, running, blocked and exit. I shall explain what are these states. So whenever a job is submitted, then it goes from new to ready state. So whenever it is ready, that means there is a possibility that a number of jobs may be in the ready state. So there may be some kind of queue of jobs waiting in this ready state. One of the job, usually in round robin fashion, since there is no priority, in a round robin fashion, a particular job is selected and it goes to a running state. That means it is dispatched to the CPU for execution, and here it is essentially you are admitting it as a job to be executed. So it goes to the running state. Now when it is running, it is not allowed to run till the completion, so that it does not monopolize the CPU. What is done? There is some kind of time slice. Some kind of time slicing is used, uh, and the time slice is not very big, and for that duration it is used to run. And within that time slice, if the execution of the job is not complete, again it is returned back to the ready state. So we can say this is timeout. When the timeout takes place, it is again returned back to the ready state. So the execution job is partially complete. It is not yet fully complete. However, if it is fully complete, the job goes to exit state and it is released. So it goes to exit state. That means the execution is over. Now, when a particular job is running, it may happen that it requires some I/O processing. So whenever it wants to do some I/O processing, obviously it cannot keep the CPU busy. So it comes to block state, and we can say an event wait has occurred. That means CPU has to wait for that I/O processing to be over, and after the I/O processing is over, again it goes back to the ready state. So you can say event has already occurred. That means I/O processing, data transfer from the memory and I/O has taken place. Event occurs. So this is how a number of jobs or tasks are executed one after the other in a time sharing system. The advantage here, as you can see, the jobs are divided, and if we consider this as the time, each job is allocated a very small fraction. Say this is job J1, job 1, then after a very small time gap, which is known as uh, tasks, that in between execution of two jobs some time is needed, that is known as context switching. Then another job is executed. So in this way, one after the other in a round robin fashion, each job is executed. Now what is the advantage of this approach? The advantage is that it has got short turnaround time. Why short turnaround time? Here you see each job is given a small fraction of the time, and as a result, if the job is small, very quickly the execution will be over. It need not wait for the execution of all the jobs or all the tasks. Some of the tasks may be very big and may require very long time. So the a short job will not take long time. However, a long job, a big job, will take some more time. So it has got short turnaround time, and it gives you much better CPU utilization. So CPU utilization is much better. Moreover, it gives the impression of some kind of parallel processing. Each user feels as if he is the sole user of the machine, although he is getting a very small fraction or a small slice of the time of the CPU. So some kind of parallel processing, although it is not really parallel processing, some kind of illusion of a parallel processing, uh, that feeling of parallel processing is user feels that parallel processing is taking place. So uh, these are the main advantages of this time sharing system. So here you see we are doing task scheduling, task or job, whatever you call it. Is preemptive. In the previous two cases, we have seen that in the first case, for example, when a job is executed, it is executed from the beginning to the end, irrespective of the time it requires for execution. And as a consequence, there is a possibility of monopolization of the CPU time. Here it cannot take place because you can see whenever timeout is taking place, the job is irrespective of the time required by it, it will be stopped after a very small duration. This fraction of time is relatively of the order of few milliseconds, not a second or hour. So for a small duration of few millisecond, each task is executed in a round robin fashion. So this is known as the time sharing system, and this is the kind of operating system used in most of the modern processors. However, this particular time sharing system cannot satisfy the requirement of the present day embedded applications, and because some of them are real time in nature. Before we discuss the real time operating system, let us have a look of the characteristics of the subtasks which are essentially to be performed by embedded applications in embedded applications. First particular feature is subtasks do not require equal time. We will find that different subtasks will require different time. Usually a big and complex task is broken down into a number of subtasks, and the subtasks, all the subtasks will not require equal time. That is one important feature. Some subtasks will be small, some subtasks will be long. Another important feature is some subtasks are periodic in nature. Even in the last lecture, we have considered two applications. There we have seen that acquiring data from the ECG machine was that particular task was periodic in nature. So in many embedded applications, you will find that some of the subtasks are periodic in nature. They will occur at regular interval. However, the interval may not be fixed. Second thing is some subtasks are asynchronous in nature. Some of the subtasks are originating from outside. As a consequence, they may be occurring at any point of time, which is known as asynchronous. That means some of the subtasks will be asynchronous in nature, will occur at any time. So we have to take care of those asynchronous subtasks. Then some subtasks have higher priority, particularly the subtasks which are real time in nature. They have to be given higher priority. For example, you are controlling a missile or an anti-aircraft gun. So for firing to pull the trigger and firing, that is a real time job. So once a target is found, you have to trigger within some deadline time. So that's a high priority task. On the other hand, to display some information on the monitor or on the LEDs, those things are not of high priority. That means some subtasks are of high priority, some are not of that high priority. Second thing is some subtasks have deadline time. So far, we have assumed that all the tasks have to be executed. They have to be executed correctly, but it is not necessary that they should satisfy some time. That means time constraint or deadline. But we shall encounter many applications where there will be a deadline time. If the task is not executed within that deadline time, or an event is not performed within the deadline time, Either it will lose its value, lose its importance, or it may lead to some catastrophic situation. So, the deadline time will be very important. Some subtasks are triggered by an event. Obviously, you will encounter some of the subtasks are originated because of the occurrence of another task. That means the task is triggered by an event, external event. So, that also has to be taken into consideration. Then final characteristic is some subtasks occur after a time interval. That means you have to maintain some time interval, and after some time interval, say there will be a suppose you want to trigger after 2 seconds, trigger an event after 2 seconds or 2 minutes or like that, and that kind of subtask will also be encountered. So, these are the natures of the subtasks, particularly for real time embedded applications, which are to be implemented, and to support the implementation we have to develop an operating system known as real time operating system. Let us see what are the important requirements to be satisfied by the real time operating systems. Obviously, the time sharing OS is not suitable operating system is not suitable. Why it is not suitable? The reason for that is we have seen that time sharing operating system uh, treats all jobs equally. There is no priority, there is no deadline time. That means in time sharing system all jobs are having same priority level. That is why the real time tasks cannot be are not suitable for execution with a time sharing operating system. And uh, the real time applications real time application require requires timely response. As I mentioned, they may have some deadline time. So, that time without timely, if the time is not maintained, it will lead to some problem. Usually, the tasks are classified into two types. One is your hard real time system, hard real time task. Another is soft real time task. So, these are the two types. In the first case, failure to meet deadline may lead to undesirable damage. As I mentioned, it may lead to some catastrophic situation, or the result that is generated will be of no value if it is generated after the deadline time. Either of the two can happen. So, in such a case we call it hard real time task. So, in the second case, some of the tasks it is desirable that they complete the task within the deadline time, but if the deadline time is not maintained, still it is tolerable. It will not lead to undesirable damage. Maybe some degradation in the value may take place. So, these are the two categories of subtasks are to be taken care of by using real time operating systems. What are the features to be supported by these subtasks? Usually, let me take a separate page. The real time operating system RTOs should have the following features. What are the features? First of all, creation of subtasks for a single application. That means an application, a complex application, is to be broken down into a number of subtasks. And obviously, you have to break it down and group them into separate a group of subtasks. And for example, all the activities which have the similar time functions, that means deadline times to be met, are to be grouped in the same category, or say activities with different deadlines should not be grouped in the same subtask. That means grouping and ungrouping has to be done carefully. So the subtasks which are performing similar functions may be grouped together. Subtasks performing requiring similar times should be grouped together. However, subtasks requiring different deadline time should not be grouped together. So uh, uh, this kind of subtask grouping has to be done with the help of this real-time operating system, and RTO should support that. Then it should be able to assign priority, ability to assign priority. As I mentioned, some of the subtasks will have higher priority. That is one of the requirement. So the real-time operating system should be able to assign priority to different tasks, and it has to be user defined, priority of interest, priority of interrupts. As you will see, the interrupt will play a major role, and in this case the priority of interrupts has to be interrupt user defined, and all the tasks will have different priority that will be implemented with the help of interrupts, and they will have some priority, different priority levels. So you'll be assigning priority, and the priority is assigned with the help of interrupts, and interrupts will have different priority levels that you should be able to do with the help of this real-time operating system. And finally, another important feature should be there is the task scheduling should be priority driven or deadline oriented. What does it mean? The task should be scheduled by taking into consideration the priority levels and also sometimes taking into consideration the deadline times. Let me take up an example to illustrate the uh, that deadline time oriented scheduling approach. This is essentially based on EDF. EDF stands for early deadline fast. So here you see there are three tasks. They are asynchronous in nature. Task T1 arrived at time T0. Task T2 arrived at time 4, maybe 4 seconds, some time unit. Task T3 arrived at time 5, and each of the tasks has some duration of execution. Here is the duration of execution: 10 time units for task T1, 3 time units for task T2, 4 10 time units for task T3. And here are the deadline times. That means after the arrival, I mean these are the absolute deadline times. That deadline time is 33 time units. Here it is 28 time units and the 29 time units. So here A task scheduling algorithm based on early deadline first is shown here, and how the scheduling is occurring is explained here. Here you see the task T1 has arrived in time T0, so it will be scheduled first. So T1 will be executed up to 4 time units, and after that time T2 arrives, which has got uh, a smaller deadline time. That means since the deadline time is fast, that means 28, it has got shorter execution time, but that is not the criteria. Here the criteria is early deadline fast. So this 28 time unit is the earlier than 33, so it is scheduled. That means the task T2 is scheduled, and task T1 is preempted at this point at time unit 4. Then it will take 3 time units to execute, but before the when the execution was going on, that task 5 occurs at time 5. Here it arrives, but it is not scheduled because it has got deadline time higher than the task T2. So task T2 continues, and task T3 waits, and only after the execution time is over for task T2, again it checks which one has the earliest deadline time, T1 or T3. We find that T3 has earliest deadline time, so it is scheduled here, and T3 is executed till the end, and at time unit 17, so starting from 7 to 17, 10 is the duration, it is executed. Only then that task T1 is executed. So task T1 starts execution at time unit 17 and is finished within 23. So we see all the tasks are meeting their deadlines. This is over in task T1 is over in time 23, it is over in time 7, this is over in time 17. So 7, 17 and 23 all are lesser than the deadline times. So in this example, by taking into consideration the earliest deadline fast approach, the scheduling has been done, and you see all the jobs are meeting their deadlines. So this kind of deadline based or deadline oriented approach has to be used for the purpose of meeting the deadline, for scheduling the tasks. Now whenever you implement with the help of a microcontroller, there are several approaches of implementation of the tasks, I mean scheduling of jobs. So here you see uh, one extreme is round robin. It is just like the first approach, that is your the first one that we used, uh, batch processing. Here you see task T1 is executed, then task T2, and then task N. It can be done in this manner. Here all are scheduled one of the other in a round robin fashion. Another approach is this is not done in a round robin fashion, but everything is done with the help of interrupts. That means all the tasks are assigned some interrupts, and obviously they will be having their priorities, and based on uh, the priority of the interrupts, they will uh, interrupt the processor is waiting for the interrupts, and when it is interrupted, then it is executed. So in this case, as you can see, all the tasks are interrupt driven. So these are the two extreme situations for the implementation of job scheduling by using in one case interrupt driven, in another case without using interrupts. However, in practice, it may be necessary to use something in between, not really the not really the uh, fully round robin one or the interrupt driven, as I discussed. So here is an example of task scheduling where we have combined the priority based interrupt driven and some subtasks which don't have any priority are executed one after the other in this way, in a round robin fashion, and some subtasks which have the priority, they are executed in an interrupt driven manner. So here, as you can see, after initialization of the processor, the real time operating system will schedule task T1, task 1, then it will schedule task 2. In this way, it will keep on scheduling up to task n unless it is interrupted by a high priority task. So how it happens, let me explain here. Suppose this is the mainline program that is being executed, and sometime here a high priority task is arriving sometime here. So a high priority task is arriving, and maybe sometime here, and somewhere here a low priority task has arrived. So since a low priority task has arrived here, it will start execution and it will continue to execute. However, sometime here a high priority task has arrived and it will preempt the low priority task. This low priority task preempted the mainline job. This is your mainline task. These are the mainline tasks which was interrupted by a low priority task coming through interrupts. Then here a high priority interrupt has occurred sometime here, and this is preempted, and a high priority task is executed, maybe till the completion. And after the execution of this is over, then the low priority task is again scheduled and it is executed, and after its execution is over, then the mainline task is again executed. So in this way, using the two approaches that we have discussed, they can be combined together to have the uh, priority driven as well as low priority task execution simultaneously. So we can see how high priority task is interrupting the low priority task, and the low priority task is interrupting the mainline task, and so on. This is how it will be done. Now let us consider what are the important features, built-in features that you require, that you expect from the processor to implement such a real-time operating system, or rather what are the built-in features needed in a processor that will allow easy implementation of real-time operating system. We have identified three important features which are useful in implementing or to support real-time operating system. First one is the powerful interrupt structure. What do you mean by powerful interrupt structure? First of all, the interrupts must have priority level. Interrupts must have priority levels. This is one feature that should be supported by the interrupt structure. Then there should be some mechanism to enable and disable interrupt. You may be asking why this is necessary. Suppose a task is executing a particular resource which is critical in nature. Some data it is processing, it is reading data or writing into memory, something like that. Some critical task it is performing, and when it is doing that, it is desirable that no other task interrupts the processor. So to do that, what can be done? The interrupt can be temporarily disabled, then it can be enabled when that critical task execution is over. So to support this particular facility has to be supported by the interrupt structure. Then the latency of interrupt should be small. latency of interrupts should be small. What do we really mean by this? We know that whenever a processor is having multiple interrupts, there is a interrupt priority levels. There are many interrupts coming, and whenever there are many interrupts are generated, then the processor has to identify which particular interrupt has to be serviced. If that has to be done by software, it may take very long time. So that has to be supported by hardware. Particularly that vectored interrupt provide you low latency. Vectored interrupt. Then the, as I mentioned, the priority levels can be mentioned, and it may be helpful if this can be dynamically changed. Then means dynamic change of priority levels. Second important requirement is programmable timers. We have seen that most of the tasks are time driven. Something has to be started after some time duration, and that's why programmable timers is a very important requirement of real time operating system implementation. And usually most of the microcontrollers provide the this programmable timers, because these are time driven. So, timing signals are generated with the help of programmable timers. Finally, we have seen that in case of that time, that in the task switching from one particular job to another job, some time is wasted. You have to retain the status of the job in the processor. Then whenever the old job again starts, you have to restore the status. For that, you have to, usually stack is used. That means from the registers, data is transferred to the stack or the main memory. Then it is restored from the main memory. That's a time consuming process. That problem can be overcome by using register banks. Say you have got 4 register banks, and each task is assigned a particular register bank. When task switching occurs, only you have to switch the register bank rather than save all the registers. So these are the built-in features which are supported. Now let me very quickly discuss the built-in features provided in 8051. As you know, there are 5 interrupts which are available in 8051: interrupt 0, timer 0, interrupt 1, timer 1, and serial port. So these interrupts have fixed priority among the interrupts. As we know that these are the priority levels. Interrupt 0 has the highest priority, then timer 0 the next highest, and serial 1 has the lowest priority. And each interrupts have vector addresses. As I was telling, to reduce latency, vector addresses are important. Here we find they have the vector addresses. Interrupt 0 has the vector address 0003, timer 0 has vector address 000B, interrupt 1 has vector address 0013, timer 1 has vector address 001B, serial 1 0023. All these things we have discussed in detail earlier. Secondly, then each interrupt can be individually enabled and disabled using that interrupt enable instruction. As you know, there are 2 registers, enable interrupt and interrupt priority. This is IP register and this is your interrupt enable register. Here you can see all the interrupts can be enabled or disabled by setting or resetting this bit, and on top of that the interrupts can be individually enabled or disabled with the help of this interrupt enable register. So this facility is very useful in implementing real-time operating system. Moreover, each source of interrupt can be programmed to one of the two priority levels. As we know, the 5 interrupts can have their own priority levels. Again, they can be grouped into two separate priority levels. That means suppose PS1 is 1, PX1 is 1 and PX0 is 1. In that case, these 3 are in the same priority level and these 2 are in the same priority level. And among these 3, again the priority levels are decided by this particular uh, fixed priority levels. In this way, you can see the 8051 supports all the uh, features that is needed in for support implementing real-time operating system. Finally, we have got two 16-bit timer counters with the help of which delays of suitable time can be generated. We have discussed in detail the timer counter operations, and also it has got 4 register banks as I mentioned earlier, and the register banks RB0, RB1, RB2 and RB3 can be selected with the help of this program status word register. As you know, after you reset the system, the register bank 0 is initially selected. Then by programming this, you can select one of the other 3. So if you have 4 tasks and you can assign one of the register banks to each of them, then task switching will require very small time. In other words, latency for task switching will be small. This is very important because all these latencies or delays will help, reduction in latencies will help in meeting the deadlines in implementing real-time operating system. So you see, 8051 has been provided with many built-in features which can be used to implement real-time operating system. And we have already discussed what are the important functionalities to be implemented by real-time operating system. Thank you very much.